Alright guys, so in this video we'll learn about three data structures: stack, queue, and deck. Right? So let me start with stack. Okay, so stack is a data structure. We'll be storing we'll be storing elements in the form of a stack. So if it's an element 1, it's an element 2, it's an element 3, it's an element 4. Right? So the the elements, so the last element which we have added will always be on the top, right? So because will store, because we are storing elements in the form of a stack here. Okay, so the one which we place on the which we so the one which we place on the top is the last element which we place, right? So so because this is a stack, the element which we place on the top has to be removed first, right? You can't remove 3, you can't remove 2, you can't remove 1. The element which is on the top has to be removed first, right? So so that's why this data structure is also called last in first out, LIFO, last in first out data structure, because the one which we have placed on the last, okay, when we take those elements out of this of the stack, the the element which we have placed at the top, placed at the last, is the first element which will be popped out of this stack. Okay, next is queue, right? So what is a queue? Queue is a queue, right? So if you are buying a ticket at a, so let's say if you're in a, so let's say if you're in a queue to buy a movie ticket. Okay, so first so first so the f- so the first guy so the first guy who joins the queue will be the first one to leave, right? And then the second guy who will join the queue will be the second one to leave, right? So this data structure is uh, first in, first out. Whichever element has joined the queue first will be the first one to be popped out of the queue, right? So first in, first out. Deck is a slight deck is a slight Deck is a slight modification of queue, in which you can remove, like here in queue we can only remove the elements. Um, he- so here in queue we can only remove the elements from the front, right? But in DQ you can choose, because we have because we'll write two functions there, where if you have a queue, so in a deck, you can remove the elements from front also and from rear also, depending upon the requirement, right? And you can add the element also from the rear and from the front and from the rear, right? So that's a slight modification of queue. In queue, we can only remove the elements from the front, and we can only add the elements from the rear, right? So that's the whole idea of stack queue and dequeue. Let's implement them using Python. First one is stack. So we'll use the init. So we'll use the init. So we'll use the init constructor to to initialize the stack, right? Yeah. So after that we can define the methods. So let the first method be if the stack is empty, right? So to check that, we can just return self.items, which is the array. We can just simply write we can simply return the boolean, return self dot items equals to empty, right? So if it is empty, it will return true. If it's not empty, it will return false, right? Next we can um, uh, push push an element. So self comma item, right? And self dot items. It's an array, so we can append to whatever we want to push inside the stack, right? Append item. Then we can define one more operation, pop, to extract to take an element out from a stack which has elements, right? So just self, right? Self dot items dot pop. Next, if you want the size of a stack on the stack, right? So return. Here also we need to return the element. So return length of self dot items, right? And there's one more operation called peek, which we can use to which we can declare, which we can use to find out which element is on the top, right? Just to check if I have stored several, if I have stored some elements in the stack. So I just want to, if I just want to check which element is at the top right now. So 91 is there at the top, right? So we can use a peek function uh, to return the element which is there on the top. So return um, self dot items inside bracket self dot items -1, right? And yeah, so let's execute it. Let's create a stack. So s equals to stack, so s dot push, sorry, s dot push 89, s dot push 78, s dot push 67, s dot push 43, 42, s dot push 32, right? So let's see which element is on the top. So s dot peek, sorry, s dot peek. Maybe I need to execute this again. Maybe it won't run. Yeah, we need to pass self inside it. Right. Let me execute this again. Is equals to stack s dot push 87, s dot push 67, s dot push 90, s dot push 76. Right. Again, if I so s dot peek, if I just execute it here. So 76 is the last element which we pushed on the stack is 76. So so first one was 87, then came 67, then came 90 and 76. Okay, so the 76 is one which is at the top. So s dot peek return 76. Okay, so so how is this working now? The way the indexing has been done, it's self dot items 0. This one, this is self dot items 1. This one, this is self dot items 2. This one, self dot items 3. Okay, so we have the elements here. So this is how the elements are indexed, right? So right now we have 4 elements here, right? So length of self dot items will give you the count of all the elements which are present inside the stack. So it's right now 4, right? So this will return 4, and 4 minus 1 is 3. Because it starts from 0, we need to do a -1, right? So 4 minus 1 is 3. Self dot items of 3. So we have 76, right? So so 3 will be the index of self dot items, so which will return self dot items 3 here, right? Now, and same for length of self dot items, that will give us 4. Let's see if I return self dot items. If I return the size, s dot size, will give us 4, because there are 4 elements. Now, if I want to pop something out, right? So if I pop something out, the last pushed in. So if I use the pop function, the element which it should return, which it should return, should be the last one, right? The last element which we have pushed onto the stack. So s dot, if I execute s dot pop, yeah, 76 was the last element which we pushed onto the stack, and it returns 76, right? Is the stack empty? Let's see. S dot is empty. No, it's not empty, right? If we pop everything else, pop the last one. Right now, if I execute is empty, yeah, because we have popped all the elements out, right? Now, so this is how stack works, right? Now, so we'll see a similar implementation while we are trying to create a queue data structure. Okay, so I just clear out everything. Okay, so for queue, again, let's declare a class and queue object. All right, definition init self, okay, self dot items equals to, will declare an empty array here. All right, initialize the queue, right? Next, let's check if the queue is empty. This, so it should return self dot items equals. Next, add. Okay, so add item should here will add the elements to the queue, which will always be from rear, right? Which will always be from rear, not from the front. Okay, so to add this from rear, we have to self dot items, we need to insert at the 0th index. All right, item. To remove self item, no, we don't need item here, because remove, we don't have a choice, we don't get to choose in a queue that which item we want to remove. It will remove from the front only, right? So self dot items pop, that's it, pop, and size, self inside it, so it should return len self dot items, right? And okay, one more thing, like the add operation in queue is enqueue, right? And remove operation is deque, right? So let me execute this. Let's create an object. So queue dot enqueue, add 24, queue dot enqueue, add 45, queue dot enqueue, 87, q dot nq 90, right? And q dot, so this is how it will get added, right? 24, 45, 87, 90, right? So if I use the pop, it should should remove it should remove 24, right? Because because 24 is on the front right now. Okay, so q is first in, first out, right? So 24 came first, so it should be the first out. Let's see if that works. Q dot deque. Okay, we haven't returned it. So 24, 5, 87, 90 should return 24. Okay, so 24 it will return, and we add the elements using enqueue. Let's check the size. So q dot size give us 3, because there are only 3 elements, 90, 87, and 40. Let's modify this to create a deck. Okay, now let's implement a deck class, deck object, right? I'll initialize this using an array equals to. Now check if the deck is empty. We'll implement is empty self, so it will return self dot items. Okay, definition. And now, what did I tell you about a deck? That you can, it's like a queue only, but you can add from rear also, you can add from front also, you can remove from rear also, you can remove from front also. So we'll we'll develop all these functions. Add front self item, right? So to add it at the front, it's very simple. Self dot item dot append item, right? To add it rear, here instead of append we use insert at index 0, right? And remove, if you want to remove it, self, so from the front it's same as just have to mention pop, but to remove from rear, self dot pop, also you have to pass the index 0, right? Next is maybe size, right? Size self or items. Okay, then so return it, return all these values. Here we need to return, here we need to return, here also we need to return, insert append. Now if I execute this, let's make an object deque t dot, let's say add front 23, that works. T dot add front 56. Okay, it works. D dot add front 78. It works. D dot add. Now, I want to print this. Maybe I need to add a function to print also. So, traverse for LA and self items. Okay, so if I d dot traverse, right, so 23, 56, 78. Now, if I do an add front 90, if I traverse it again, so it gets added at the front. Okay, so you can look at it like this: 23, 56, 78, and 90. Right now, if I add something at the rear, add rear 32. If I traverse after that, it gets added here. It gets added here. Okay, when we added 90, it got 90 was added here, and when we added 32 as a rear, it got added here. Okay, now let's try the remove functions which we developed. So d dot remove front, right, 90. So this one got removed. All right, 90 got removed. All right, and d dot remove rear 32 got removed. Okay, so when we use remove front got removed, and when we use remove rear, rear got removed. All right, so so we tested all of them. Okay, if we talk about size, so d dot size, 3 elements: 23, 56, 78. 23, 56, 78. Right. So I hope you got an intuition of how these three data structures work, and so I hope you got an intuition of how these three data structures work, and how to implement them in Python. So we'll definitely see how we apply these data structures to real programming scenarios. But for now, if you have any doubts, or please leave a comment, and subscribe to this channel for more videos on programming. Yeah.